Welcome back to Physics 151 Online. Today I'd like to do an example of a problem involving two-dimensional motion. Again, the simple case where the object that's moving is in free fall. It's under the influence of just the Earth's gravity. So here's the problem. An airplane flies parallel to the Earth's surface at a speed of 80 meters per second and a height of 300 meters. In order to drop an instrument package out of the plane so it reaches a team of scientists on the ground, how far away horizontally should the plane be from the scientists when the package is dropped? Ignore air resistance and assume the package is in free fall, and in particular we're going to assume there's no parachute, so the package just falls towards the Earth under the influence of gravity. And we should always start with some kind of a sketch. My sketches are not going to be great works of art by any stretch of the imagination, but here's my attempt to sketch a plane in flight horizontally. Okay, and we're given what that initial speed is of 80 meters per second. We need to draw the ground and the basic. Oh, that's not very good. Let's try that again, see if I can do a little bit better job of a horizontal ground surface. Here's the scientist on the ground who wants to receive this package. The package is going to be dropped from the plane as it's moving horizontally, and we'll set up the X and Y axes the way that we normally would. That's always a good thing to draw into your sketch, where Y is positive in the upward direction and X is positive towards the right horizontally. Alright, so we also know the height, the initial height here is 300 meters up there, so I'll just draw that in, 300 meters, and it would be a good idea for qualitative purposes to sketch the trajectory. And so as the parcel is dropped initially, and this is very important, it has the same initial velocity as the plane itself when it's just dropped out. So it will start off traveling horizontally and then will arc down in a parabolic trajectory towards the Earth's surface. And so what we're trying to find is what's that horizontal distance that the plane should be away from the team on the ground, and I'll label it delta x, in order to have the package that's dropped reach those people. So we can make a list now of given information. We know the trivial stuff for a problem like this. We know that the acceleration in the x direction is 0. The acceleration in the y direction is negative g. We'll plug the numbers in for that later when we're ready. Also, as I just discussed, we know that the x component of the initial velocity is what I wrote down as v0, which is just 80 meters per second, so that's given, and v0y is equal to 0, because the initial velocity right when the package is dropped is only horizontal. There's no vertical component to it. Another way of thinking about this is that the initial angle is 0, right? So the x component will have a cosine of the angle, which is 1. The y component will have a term involving the sine of the angle, which is 0. Alright, we also know what delta y is. And if we think carefully, okay, the delta y is y final minus y initial, which means that that delta y is negative 300 meters. Delta x is what we're trying to find. So there's not really anything else that we can write down, and I've already included this in the sketch, but we're trying to find delta x. So once again, the clue in a problem like this is what's given but also what's not given. Here there's no information given about time, and so the strategy will be once again to write down the equations for constant acceleration motion for delta x and for delta y and combine those by eliminating the time variable. So we know that this is v0 x t. There's no acceleration term because the acceleration in the x direction is 0. So that's my equation 1, and I'll go ahead, since I know what I have to do, I'm going to solve for time in this equation, delta x over v0x, like that. We'll call that equation 1. Equation 2 is the expression for delta y, which is v0yt minus a half g t squared, where I've already plugged in that a sub y is equal to minus g. That's equation 2. I'm trying to solve for delta x, so let me solve. Oh, and of course what I see right away is that v0 is equal to 0. So that term goes away, that's equal to 0. So let me rewrite equation 2 and substitute equation 1 into it. Alright, so sub 1 into 2. What will that give us? That will give delta y is equal to negative half g times t squared. So t is delta x over v0x. That quantity gets squared, and when I do that, I have g times delta x squared over, actually minus g times delta x squared over 2 v0x squared. And all that's left to do is to solve for delta x, because everything else that's in that equation is known. Solve for delta x, I will get, alright, I'm going to have to solve for the delta x squared term and then take the square root of it. And I'm going to go ahead and do that all in one step. Make sure that I don't blow it somehow. That delta x will be a square root of some kind of a fraction term. So delta x, it'll have, the negative sign will be in there, right? And then it'll have 2 delta y v naught x squared in it, right? All under the square root. And the denominator term will just be g, if I've done that right. Alright, so that's my solution for delta x, and now and only now am I ready to plug numbers in for these quantities, delta y, g, and v0x. If you plug in numbers into the algebra at an earlier stage, then every algebraic step you make, you have to keep rewriting the numbers, and it's really easy to drop something out, to copy it wrong, and to make a mistake. I would prefer to always just plug the numbers in once at the very end when I'm ready to solve for the desired quantity, which here is delta x. So I'll substitute these numbers in. Negative 2. Okay, if that minus sign is bothering you, remember that delta y is negative 300, and so we can find, or we can plug that in. Where's my, where did my pen go? Ah, there it is. Okay. Negative 300 meters. Alright, and then we've got v0x squared, so that's 80 meters per second, quantity squared, all under the square root, divided by the familiar 9.8 meters per second squared. Let's take care of the units first. Meters cancels with meters. The seconds inside this term is going to get squared, so seconds squared cancels with seconds squared down here, since they're both in the denominators. And what I have left, if I just move this over here, will be in units of meters squared, because I have meters. The 80 meters per second squared gives me a meters squared, but the square root of that will give me just meters. So it has the right units, and if you substitute these numbers in, the two minus signs cancel, and I get 626 meters for the answer. And remember that there's always a step at the end where we look at the answer and ask, does it make sense? The first thing, since we've plugged the units in, we can say, yep, the units make sense. I know that my answer is supposed to be a length. Delta x is supposed to be a length, and I get an answer in meters. That makes sense. The value, again, this is not something where we can determine whether it's a reasonable value with perfect accuracy, but since the package was dropped from 300 meters, it seems to make sense. It's on the right scale to have a value that's several hundred meters. So I'll just say that value, whoa, that's getting close to the edge of my tablet. The value makes sense. Sorry about that mess. So those are about the only two things that we can do to assess this answer. Hopefully this gives you, yet again, another example problem. Notice that this very common method of solving for time in one of the displacement equations and plugging it into the other one has been used once again. Now before I finish, I want to also just mention something about a good problem-solving technique that that you should be able to see here on my PowerPoint slide. And what I want you to see is that when you solve problems, whether that's in your problem-solving notebook or whether that's in a quiz or an exam question, it's always good. You don't necessarily have to rewrite the problem statement, but it's always good to draw a sketch where you clearly label the given information, and then to put in some words to explain what you're doing, where an equation comes from, to write down the important kinematic equations to start with before you substitute in specific values, number your equations, and then when you combine them, you can have a little statement like I usually do where I say plug equation 2 into equation 1, carry out the solution, and then only at the very end you plug in the numbers. And a couple of things to remember is that as I said, draw clear sketches, leave plenty of space between steps, explain what you're doing, and then evaluate and explain your results. There are cases where you might, as in this problem here, where you might have two solutions when you're using a quadratic equation, for example, and one of them you're going to keep as a physically meaningful solution and the other one you'll discard. And then finally, once again, a reminder to include units in calculations and have some kind of evaluation statement about your answers. All right, one last thing. If these kind of problems have been challenging for you in this part in the course, don't be surprised and don't feel like you're doing something wrong, because as I've already mentioned in class, there's this statement, problems worthy of attack prove their worth by hitting back, and only solutions to those problems that are really kind of challenging give you satisfaction that you've really understood things. And one other statement that I'll include, which is important to keep in mind when you're studying something complicated like physics, is this: subjects which disclose their full power, meaning, and beauty as soon as they are presented to the mind have very little of those qualities to disclose. So, one of the reasons that it takes a while to really get the hang of learning physics and using physics principles to solve problems is precisely because there is power, meaning, and beauty in trying to understand the behavior of things in the natural world. It takes a while because there's a lot there, and the quest is worth it. I hope, even though you might not love physics the way that I do, that you do begin, as we go through the semester, to appreciate some of the beauty, some of the real excitement of solving physics problems. And I'll see you in class.